Hello, advanced physics students. This is Dr. Brenzy. I've been looking at your lesson, or excuse me, your Unit 8.1b formative corrections, and I've been noticing a lot of common errors that I want to address because they're going to greatly affect your performance on the summative come on Monday. So, I want to start by talking to you about signs. Especially when we have signs involving a point charge, so signs on vectors. Okay, so when we're dealing with force or electric field involving a point charge, so that is a single point that has a charge on it, the force and electric field, the sign that comes out from the equation tells you direction, but it doesn't tell you direction in a left or right sense. And a lot of us have forgotten about that. So let me show you what it does tell you. So let's start with force. So we have two charges, and we know that we can use Coulomb's law to figure out how much charge, or how much force is being exerted on Q1 by charge Q2. So how hard is this being pushed, and in which direction? That's what we're ultimately asking ourselves. Let's say, for example, that, when you calculate this number and you get a positive number, that positive number doesn't mean it's going to the right. That positive number is telling you that means that the force is pointing away from the other charge. Now that's not where you're used to, but when we're talking about Coulomb's law and point charges, we have to start thinking about positive and negative in a different way. So positive means away from the other charge, no longer means right or left. So if we have two negative charges, well, when we plug that into our Coulomb's law, we're going to get negative times negative, which gives us a positive number. That positive number tells us that charge Q1 is being pushed away from charge Q2. So if we had to draw a vector for the force of Q1 or Q2 on Q1, we would draw this vector right here. It is actually pointing to the left, even though we got a positive result. It's because positive means away from the other charge. If charge Q1 had been over here, then our force would be pointing again away from charge Q2, but this time it just happens to be pointing toward the right. Well, let's erase that and let's think about what negative means. So if we get a negative number for this, instead of a positive number when we plug in our charges and our distance, then that negative number means that the particle, the charged particle, Q1, is being pushed toward charge Q2. So if I have a negative and a positive charge, and I use Coulomb's law to calculate the force of Q2 on Q1, I'm going to get negative times positive, which gives me a negative result. Now, one thing I forgot to explain, and I should probably do that at this point before I go on, is what do I mean by negative times positive? Well, it's obviously the sign of the two charges. So this number would be negative, that number would be positive. It turns out that those two are the only two that can possibly have a negative value. All of these other variables, k is a positive constant, and r squared is a positive number because any square is a positive number. The square of a real number is a real number, or a positive number, excuse me. So in this case, Q1 is being pushed toward Q2. So that would be the direction of the force. If we put Q1 on the other side, then we would actually point our vector toward the left, because that left direction happens to be the direction toward the other charge. Okay, let's talk about what signs mean in terms of electric field and its direction. So when you have electric field, you only have one charge, and that charge is producing an electric field, and that electric field can be positive or negative. So let's say that we want to figure out what the electric field is at this point right here. So if I get a positive number when I use this formula for the electric field, that means that the electric field vector is pointing away from the charge. So in this case, the electric field vector would be pointing toward the left. If I were interested in the electric field at this point, again, it's pointing away from the charge, so that means, in this case, the electric field is pointing toward the right. Now let's think about what would happen if this number turns out to be negative. Well, in that case, that means that the electric field vector is pointing toward the charge. So if I want to know the electric field here, and it turns out that this gives me a negative number, that means that the electric field is pointing toward the charge. Likewise, if I were interested in a point on the other side, again, my electric field vector would point toward the charge. So when you're dealing with point charges, the really important thing to remember is that the sign of your vector, the sign of your vector tells you away or toward. It doesn't tell you left or right. In order to figure out left or right, you need to use a diagram. So let's look at some examples from the formative that actually bring this into play and actually caused a lot of students confusion and wrong answers, as well as some bad corrections, I got to be honest. So this is problem number, I want to say this is problem number 2. No, I'm sorry, this is problem number 1. Okay, so the very first problem. So this problem is asking, what is the magnitude and direction of the electric field of charge Q, this charge right here, at this point P, which is 1.2 meters in this direction. So I want to know, what is the electric field here? Okay, I use my electric field equation for a point charge. That's K times Q1 divided by R squared. And I plug in my values. I know K is a constant. I know the charge Q1 is 335 nanocoulombs. And nano means 10 to the negative 9. And then I divide that by 1.2 meters squared, because that's the distance between them. And when I crunch those, I am going to get a positive 218 newtons per coulomb. Well, that in itself doesn't tell me that this is going to the right. What this is telling me is that it is going away from the charge. Okay. And by the way, just by seeing this number, we could have eliminated C, D, and E, which a lot of us did. But like I said, the direction, this positive number, tells us that the electric field is away from the charge. Away. So if I were to draw an electric field vector at this point, it would have to be pointing away from the charge, away from point Q. So that would be my electric field vector. It would be pointing in toward the left. So my answer should have been A for that reason. Okay. So remember, when we're dealing with point charges, positive means away from the charge, negative means toward the charge. This is number 2, and this doesn't exactly have to do with direction of vectors, but it is one that a lot of us ended up missing, because a lot of us didn't realize that when you have an uncharged sphere, that means that its charge Q equals 0. And if you were to plug that into Coulomb's law, or actually write down that F equals Q times E, you would recognize that the charge is 0, which means the force has to be 0. So, this is the correct answer. And it's all because electric field doesn't affect anything that has a charge of 0. Okay, I believe this one was number 4, and this one was another one that causes some confusion because we didn't completely understand electric field and what it represents. So we have a beam of electrons, and electrons are negatively charged. I think we all understand that. Now, a lot of us are confused about what electric field is, okay? And I have in the past been saying that an electric field shows you which direction a positive charge would be pushed. And that's true. So if I had a positive charge here, it would be pushed down. What happens to a negative charge? Well, it gets pushed in the opposite direction, which means up. Now, another way to think about it was when we were drawing electric fields, we were always drawing them from the positive to the negative charge. So this plate up here has what type of charge? It has a positive charge, because that's where the electric field is coming from. It's going to this plate, so this plate has to be negatively charged. Well, what does an electron, which has negative charge, want to do once it gets near other negative charges? Well, it wants to run away from those charges. It is repelled by these charges. What does it want to do when it gets close to these positive charges? Well, it is attracted to those charges, so which way do you think this electron will go once it enters this electric field? Well, hopefully you now understand that it is going to actually go up toward the top plate. So the correct answer would have been C. Okay, finally, number 8. Numbers 8 and 9 had gave people fits, but let's talk about it. So I have two charges here, Q1 and Q2, and I am interested in finding the magnitude and direction of the net electric field at the origin of this graph. Well, the origin is where 0 is, so I'm going to draw on my diagram, hey, this is where I want to find electric field. Now, when you have multiple point charges, we have to figure out the electric field from each charge one at a time. So let's start over here on the left with this charge Q1. And, well, I forgot to write the equation, but you can actually look back at problem number 1 if you need to remember what the equation is. It turns out to be K times Q1, that's K, Q1, divided by R squared. Notice that even though that this is at a position of -3, it's going to get squared, which is going to give us a positive result. So we have positive 2,597 newtons per coulomb. Well, do you remember what this sign positive means in terms of direction? Hopefully you remembered it means away from the charge. So this electric field is pointing away from Q1, which means in our diagram it's pointing toward the right. So this is why it's extremely vital when you're dealing with point charges to draw a diagram. And as you calculate the electric field or the force of each charged particle, I would actually write that on where you are interested in finding electric field of force and actually showing its direction. Let's do the same thing for the electric field from charge Q2. Now, which way will the electric field be pointing in this case? Well, again, it's going to be away from Q2. But in this case, away from Q2 means toward the left. So this electric field, the electric field from Q2, is actually pointing toward the left. The electric field from Q1 is pointing toward the right, even though they both have a positive sign in front. That's where we have to be very, very careful. Like I said, as we draw or figure out each electric field and figure out its sign, it's a very good idea to draw a diagram when you're working with point charges to figure out which direction each electric field is pointing. Now we can finally say the diagram shows us that E net is equal to 1,812 newtons per coulomb. I forgot the per coulomb part. And that is pointed toward the right. We can definitely say toward the right because we've drawn a diagram and we know that this vector has a bigger magnitude than that one. So when we add these two vectors together, we're going to get a net result that points toward the right. So, very, very, very important to draw diagrams with electric field and force, especially when we're dealing with point charges. And to remember that positive means away from the charge, negative means toward the charge. Okay, I look forward to seeing you Monday and hope that this helps you with your summative. See you then. Bye.